Hi everyone, I'm Kushal Chawla. I'm a PhD student at the University of Southern California. This work was done with Dr. Niyati Chhaya when I was a part of Adobe Research in Bangalore, India. Let's begin. Users today have diverse and dynamic content preferences online, and in this paper, we argue that to adapt their digital experiences, not only their web journey, but also the instantaneous analytics can be crucial. So as an example, let's say this is the web page which is next shown to a user, and the local preferences of the user are for basketball, which is an outdoor game. But globally, people prefer soccer and also chess. Soccer is an outdoor game, chess being an indoor game. So user might go next for football or soccer, which is a combination of both local and global preferences, which is still an outdoor game, but is globally more preferred than basketball. So with this motivation, we aim to explore if we can leverage these local and global content preferences to better understand the future behavior of the users. And in fact, we show that we can do that using a system called DRS-LAG, which is a reinforcement learning based system and incorporates both local and global content preferences of the users at that particular instant. So here we present the main architectural details of DRS-LAG. So we model it as a Markov decision process, and we use a deep model-free Q-learning based approach. On the right side, you can see that this is the architecture. This is the architecture which our agent follows, given a state, which is a combination of content and analytics. And when I say analytics, it's the instantaneous analytics of all the web pages visited by the user in the current session. All right, and we use recurrent neural networks to combine them. So given this state and any action, and every action is a web page again, which the agent will predict that the user will go to next. A web page is again represented by content and analytics of that web page. And for every such pair, the agent or the architecture would produce a Q value, and agent would finally pick up the web page which has the maximum Q value. And then the user, as a part of the environment, will give the reward, and the reward will be in terms of what the user actually clicks. And we capture the both the content and analytics of that clicked web page as well. And then the agent moves on to the next state, and this is how it continues. So next we present the pseudocode of how we can train DRS-LAG on the offline logs. The first step is to initialize the replay memory and the model along with the web page pool and analytics so that the model can keep track of instantaneous analytics of these web pages. First step in each iteration is to fill up the replay memory with both positive and negative samples from the offline logs. Positive samples are coming from the web pages which the user actually clicks in the data, and we randomly sample some negative samples from the data as well. And along with that, in every iteration, we sample a batch from the replay memory and train the model on it using the Bellman equation. Finally, we update the web page pool and the analytics associated with those web pages after every episode and every iteration. And this helps the model to get access to the instantaneous analytics of these web pages at every point in time. And this is done in both training and testing time. Moving on to the experimental setup, our data set, as I mentioned, comes from clickstream data from particular sports website. We have close to 34,000 user sessions in training and 2,000 in both validation and testing. Path length we keep in 3 to 50 and close to 1,500 unique web pages. One thing which I want to point out is that we use a universal sentence encoder for content representations. This allows us to tackle the dynamic growth of the web pages. So instead of using a one-hot representation, we use a pre-trained method here. And for web page analytics, we track the number of views as the KPI. and we only look at the past 50 intervals, the value of that KPI in past 50 time intervals. We define the interval by 5 seconds, by using 5 seconds, and the reward which the agent gets from the environment is one, whether it makes the correct prediction or not, and second, we also want the model to maximize on the average, on the change in KPI value, so that the model is focusing on the global preference as well. We also present some hyperparameters at the bottom. To evaluate our system, we use a combination of both offline evaluation. In the offline setting, we predict the model for next page prediction task. As you can see in the recall values, the DRS-LAG system performs better than majority baselines, and also performs better than the next two baselines, which are just using the content and are not using the global analytics at that particular instant. On the right side, you can see the online setting. You built a simulator so that we can see how much reward the models can accumulate. And then, since it's a simulated setting, we can control for the session length as well. And in all the four cases, DRS-LAG helps over just using content or just the majority baseline. So just to conclude, I presented our system DRS-LAG, which can incorporate both local and global content preferences in predicting future user behavior and also potentially dynamically adapting them. As a future work, what if we incorporate other KPIs such as number of exits and time spent? And it would be interesting to see what they tell us about web pages and how we can adapt future experiences using that. Thank you.